we're good to go. So, all right, here we go. Nope, that's not the website. That's the local build. My goodness, I am all over the place. It's almost like it's the first day of, it's almost like it's 8:30 on the first day of the semester, right? All right, here we are. So I'll get to the GitHub notes in a moment. For now, let's just go down to the outline. So, evolutionary computation, it's a weird thing. I mean, really briefly, it's the idea that, like, well, if I start with a bunch of, I don't know, like randomly generated solutions to some problem I'm interested in solving, they're all going to suck, right? Like if I just start with just a bunch of randomly created things, they're not going to be very good. But some might be slightly less terrible than others. Like if I made 100 random solutions to some problem, they're going to be terrible. But some might be just a little bit less terrible, right? So the idea is, if I take from that population of 100, those that are relatively less terrible, kind of mix them together and pull them apart and put them over here and do that until I get another 100, maybe they'll be, that population, that new 100 might be a little bit better than the previous one. That's the whole idea. Except you do that like 1,000 times, maybe a million times. And at the end of the day, you actually get pretty good solutions. Now, I will say, you're not going to use evolutionary computation to solve many types of problems. You use evolutionary computation for problems where you go, I got nothing else. I don't know what to do. So I'm going to throw this at it. Evolutionary computation is in the class of algorithms called computational intelligence. You may have not really heard that word before. But it's in the same class of algorithms as like your deep learning, your neural networks, okay? If you've got some arbitrary problem that you want to solve, you don't want to use a neural network. You don't want to use evolutionary computation. You don't want to use those things. You don't want to be working on problems where you need those things. If you can find a way to solve or find good solutions to some problem you have without using things in the realm of computational intelligence, do that. But every once in a while, you're stuck. Every once in a while, you're like, well, I got nothing else. So you go to that scary place of computational intelligence, you grab one of those algorithms and you hope for the best. That's where you use this stuff. Throughout this course, we're going to be using these algorithms on toy problems for the most part. Now, toy doesn't mean trivial. They just mean like a well-understood problem where it's a little easier to reason about what might be good and what might not be good, and what changes could be effective and not effective. It doesn't mean they're trivial. In fact, far from it, most of them. Some of them are trivial. They're just well-understood problems, so it's a little easier to learn by working with those problems and learning a new algorithm. So just be warned. But in general, you're using this for stuff where you go, I don't know what else to do. I'm stuck. That's evolutionary computation. Prerequisite, 255 and 223 or 275. I don't even know what 223 and 275 is. Anyone know? Data science? Okay, cool.
And the other one is database management.
Database management? Okay, good stuff, good stuff. All right. This is me, office hours. Oh, this is wrong. I need to update this. My office hours are actually like, I'll update it. They're in the afternoon. So I got to fix that. They might be updated on the index, I don't know. Class times, this is also wrong. Got to fix that. Okay, textbook and lecture notes. So the lecture notes are this website. okay? They are derived from this textbook's lecture notes. This is actually one of the older, this is like the first edition's date. There's a second edition. I believe if you do some Googling, this is a very easy to obtain book. Just saying. Student evaluations. Now, here's the interesting bit. So, typically in your courses, you all start with like 100%, but every mistake you make, you lose like parts of your final grade, right? I don't really like that in general. I think it's a kind of like, it emphasizes things I don't like to emphasize, and it de-emphasizes things that should be emphasized, in my opinion. For example, when you lose marks for making mistakes, it's almost like it's a form of punishment, which really isn't the point. Because I've found, like, you know, sometimes I'm teaching classes, and you'll find some students in the class. There are some students that can get really good grades, but there are some students that just kind of like tinker and screw around and learn a lot, but maybe their grades don't work out in the end. And that doesn't really make a lot of sense to me. To me, I think it should be reverse. It should be like, if you're going and exploring and trying to learn more and do a little bit more, that demonstrates to me you've got a better understanding, like you're going to be learning more. So I like that idea a little bit more. So what it is instead, you all start with 0 in the class. But you get points, I'll call them, for doing stuff. There are a maximum of 130 points, I believe. What do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 130. There's a maximum of 130 points. 2 of these things are mandatory that you have to do. Everyone's going to give a lecture, and everyone's going to do a final project. But of course, if you obtain all of the points on these things, you'll only get 40%, which won't be a pass. So you can't really just get away with doing the only 2 mandatory things. These things, you don't have to do them. You can choose, maybe I don't want to do the first assignment, but I'll do the next 2 assignments. If you just don't do the first assignment, you could still get 100% in the course. Because you could get 30, 30, 30, that's 90, and then the 10, you could still get 100, or 99, because St. FX is 99 is the max we can do for whatever reason. So it gives you the ability to pick and choose what you want to do to obtain marks. But each individual assignment is not going to be, it's going to be, this is how it's going to work typically. This is just a general idea. Not every assignment is going to follow this, but here's the general idea. Each assignment I've shown was worth 30. If you implement an algorithm for the problem that I give you, you'll get 5 points, but you'll only get 5 out of 30. If you add some interesting enhancements to the algorithm, some that you may have invented on your own or some that you're aware of or that you learned about in lecture or whatever, you can get up to an additional 5 points. Using the algorithm to solve a more complex problem, so there's the problem I'll give you, and then maybe I'll also give you like an alternative problem where it's like, and if you do this, it's extra hard, but if you can get a good working solution for that, you can get up to an additional 5 points. Good visualizations, what did I say, additional 2 points, whatever. Again, these are kind of like arbitrary values for an example. A big part of each assignment is going to be the write-up, the analysis that you do. If you do your analysis, you'll get 5. If you do like a write-up, you'll get 5 points. The write-up will be marked, like those 5 points might be marked more traditionally, as in like, okay, it's taken into account like your prose, how compelling is your writing and clear it is and whatnot, right? If you use LaTeX, anyone familiar with what that is? 2 people, 1, 2, yeah, 3 people, cool. I'll show you. It's awesome. It's easy. It's nice. It's beautiful. If you do proper references, citations, include figures, tables, et cetera, you can get additional points. So when I'm saying you can pick and choose what you want to do, it's not just the assignments. I mean, even the individual bits inside the assignments. If you're like, you know what, I really don't give a S about learning LaTeX, I'm just not going to do it. Fine, whatever. You're not going to get those 2 points, whatever. That's fine. But it gives you the ability to pick and choose. So if you're more interested in maybe a genetic algorithm versus something like particle swarm optimization, you could say, okay, I'm going to do more of the GA, the genetic algorithm assignment, because I really care about that, right? If you have any questions about this, ask. You can ask now. You can ask later if you think of the questions. Or if you hate this and you want a more typical, like if any individual wants a more like conventional marking thing, let me know and we can figure that out. I think you're probably going to prefer this, though. Yeah? Any questions about this? Yes?
How do you feel about collaboration within assignments?
In terms of, everyone's going to have to do their own assignment. Projects, I've yet to determine if they're going to be independent or maybe in like groups or something. I mean, there's only like 10 of us, right? So, in terms of collaboration, depends on what you mean, right? There's like,
I understand we can't help each other write each other's code, but are you allowed like think tanks?
yeah, in fact, I strongly encourage that type of stuff. I would strongly encourage that, right? Because look, this is like a senior, an upper year level course, right? So at this stage, like when it comes to marking the actual assignment, like your actual code, my assumption is like you can't do any of the rest of the assignment unless you can get a working implementation, right? And the working implementation is only 5 marks out of a possible 30. With what these algorithms are and the level at where you are, you better be able to implement these algorithms. Like the reason it's worth so little is because these should be relatively, I shouldn't say trivial. That's really not right. But these shouldn't be particularly complex for your level. I really shouldn't say they're trivial. I shouldn't say they're easy. I shouldn't say they're simple. But they should not be overly complex for your level, especially considering we will have seen working implementations of each of these just on different problems. So all of the interestingness is going to come from what you do differently, how you tinker. A lot of where the interesting results come from is how you modify these algorithms, how you tinker with them, how you change certain values. Maybe you implement the algorithm slightly different than they do, but whatever. If you sit down in a room and you all just kind of like, if everyone got together and like, we're doing assignment 1 today, and you all kind of implement it and you're like, oh, I did this. You're like, oh yeah, well, I did this. Fantastic, great. That's the best way to learn. You're going to find more interesting solutions. To me, this type of stuff is more, you learn more by doing this type of stuff. And I know like that might sound like an obvious thing in a lot of programming courses, but really this type of content, the only way to really learn how to use evolutionary computation is by sitting down and hacking away at an evolutionary algorithm and seeing what happens. Then you're going to gain that intuition. In fact, this topic, it's kind of hard to teach because you just kind of get an intuition that's kind of hard to put your finger on. So everything we learn about in lecture is going to be high level to the point of explaining what's going to happen. And then there's going to be parts of these lectures where like, okay, today it's going to be more like a lab. And you'll all be sitting down and building a GA for something, right, together. Yeah, submissions, due dates. Who here knows how I feel about due dates? One person? How do I feel about due dates?
Doesn't matter if you're a minute late or a day late.
0, it's late, it's late. And here's why. A lot of people are like, oh, you're mean. Like, come on, a minute late. Here's why I assert that anyone who accepts anything a minute late is immoral. They think they're being nice, but I think they're being immoral. Because here's the reality of the situation. There's got to be a line on what's accepted and what's not accepted. When is it going to be accepted? And I say what the line is. I say it's 11:55. But if I accept at 11:56, suddenly, where's that line? Because what if someone wanted to submit it at 11:59, 12:07? I mean, where do I draw that line? Do I draw it after the 12:07? What if someone submitted at 12:30? Suddenly, where do I draw that line? Suddenly, none of you really know where that line is. So you know what's easier? Is if we just stick to the line that's 11:55. And here's the thing. Let's say you had a solution that was like, oh, it was so good, but if you had like 1 more minute, You could have made it better. Literally, like if you didn't feel rushed to get it submitted, maybe you could have made a better implementation. But maybe you took that minute and submitted it a minute late. Suddenly you get more marks than him because he followed the rules and you didn't? We're talking about a minute here, but that could matter. So suddenly I'm punishing people following the rules more than those that are not following the rules, and that just doesn't make any sense to me. So it's really simple. If it's submitted at 11:54, is it late? No. 11:55, if it's like 11:55, is it late? No. 11:56, is it late? Yes, because 56 is more than 55. It's one more, and that's late. Good, we understand. You're learning big stuff today. The number 6 is more than 5. Okay, final project. Again, like I said, I'm not sure if we'll do it in groups or not. It'll kind of depend on the pace of the course. My thinking isn't so much of like, well, if you do it in groups, you're not going to do as much, therefore you're not going to learn as much. No, that's not it at all. In fact, I like group work. I think that you can kind of come up with really interesting stuff by working together. The only thing, it's going to be more about the content of the course, how much we have left. If we can, each individual maybe does something a little bit different, we can kind of talk about it a little bit more. There might be value there. I'll see how things are going once that kind of comes up. Lecture, each student's going to complete a lecture of your choice in consultation with me, so we'll make sure it's good, but I'm really flexible. Email, yeah, you can email me. Office hours, come to office hours once I actually tell you what they are. Attendance, they're mandatory. Copyright policy, you can't copy me. I own everything, unless it's the course and the textbook stuff. You're not allowed to record me, but don't worry, I do it myself. So if you really wanted to, just go to YouTube and you can find it. Don't cheat. Cheating is going to be hard to do in this class. The only cheating I really saw in the past was people, I mean, it was easy to find. People were like found an implementation of like particle swarm optimization. They just copied it. Okay, no, that's cheating, which is really annoying because it's such a stupidly easy algorithm to implement in the first place that if you just did it, anyways. And some people like copied like reports. In fact, the most interesting one is I found a report. It was terribly written, but it also included some like LaTeX tags, which you'll learn about. But special tags you put in your LaTeX to make things render a certain way, so it looks more like math notation. And the report they submitted had this math notation. I was like, that's weird. So I Googled the math notation, because I was suspicious of this report. And I Googled the text, and nothing came up for the text. Okay, whatever. They just, English was a second language, so maybe they just struggled with it fine. I did the math, though, and sure enough, I found a web page written in another language. And then I was like, oh, well, translate. Boom, there it was. There was their whole report. And I was like, wow. And that, because I found the one with the tag, I was able to discover several other students had done the exact same thing, because I got, wise to what they were doing. I love catching cheaters. It's fun. What's up?
How have you found people use AI to write?
Like ChatGPT? So, not yet. Now, here is what I'm going to say about ChatGPT. So, officially, according to the the academic calendar, the rule is if the syllabus includes nothing about it, it means you can't touch it with a 12-foot pole. Okay? So that's the rule. And my syllabus says nothing about it. In reality, here's how I feel about ChatGPT. Now that it's recording it. If you are using it, okay, I'll give you an example. There were people last year in like 161, 162, right? They used ChatGPT to help them write code. And like in 162, 80% of the final grade was tests. Guess if they passed the course? Obviously not, right? They didn't know anything, right? And it was really obvious. But There were students in the class that used ChatGPT to help them write their code, but they did very well. You can use ChatGPT in a way to have it do your assignment. And when you're doing like 161, 162, it'll do a pretty damn good job. Evolutionary computation, it'll probably be doing an okay job with writing the code. But if you're using it in a way where you're actually learning from it while using it, then that's a good thing. It's the same thing with peer teaching and peer learning, right? You were asking about collaborating on an assignment. Peer teaching and peer learning is one of the most effective forms of learning there is. That means when you are sitting down together and learning and working on stuff, it's more effective than me talking at you. This is empirically shown. This is like old classic pedagogy, right? This is like tried and true, centuries old. We know that this is good. But then there's the problem of like, well, I don't want you to cheat, but it would be good if you worked together, but how do you draw the line? So a lot of us take the stance of, no, you can't work together, even though working together is actually really effective. Well, now you've effectively automated the process of working with someone else, just with a computer. People were effectively replacing office hours with ChatGPT. They're like, why would I go to you? I could just ask ChatGPT and it gave me a solid answer. And you're like, yeah, you're not wrong. If you're able to use it where you're gaining from it, fantastic. If you're using it where you're cheating, well, I don't think it's going to go that well for you in this course. Because here's what's going to happen. You'll see a big chunk, you saw in the point breakdown, a big chunk of your grade is actually these like write-ups and these reports, right? First of all, if you asked it to come up with enhancements for a GA, a genetic algorithm for you, it's not. Because that's novel things that you're like, I'm going to try this crazy thing. See if it works. ChatGPT is not going to do very good at that. But that's where you're getting all the extra points. Your report. In fact, if anything, if you are someone who struggles with like technical writing, if you're the type of person where you know what you want to say, you're just like, I can't. Turning that into sentences and paragraphs though, ugh. If you've got the ideas and you can have ChatGPT help you turn it into a beautifully written paragraph, do that. That's a good thing. Someone said, well, they should go to the writing center if they need that type of help. Why? Why would you go somewhere where they're probably going to give you less good help than this would do for you? So I would encourage you to do that if it makes it easier to get your ideas down. Now, if you're asking it to do a lit review for you, a literature review on some like genetic algorithms, ChatGPT is probably not going to do a very good idea. In fact, so often it makes up stuff. So it'll like make up citations that aren't even real. You do that, you're in big trouble. That is like academic dishonesty to the max, okay? So like, but if you're using it as a tool to help you do what you would be doing, do it. You'd be stupid not to. This tech isn't going anywhere. Remember, you're not always going to have a calculator on you. Yes, I fucking do. Always. Literally, if there's anything I need to know, I can find the answer to. So ChatGPT, I think if you can use it effectively, good. I think learning to use it effectively is important. But if you're having it write your reports, I don't think it's going to go very well. Because you got to do like an analysis on what you did, right? It's not going to be able to do that. Not yet. Maybe in a year it can. I don't know. But in a year we'll figure that one out. Any questions about that? But officially you can't use it. Okay? Cool. This is all kind of the boilerplate stuff. There we go. Any questions before we go on to the first topic? Yes.
So what you were saying there about like using it to write your report, does that also go for like LaTeX formatting and stuff?
If you can use it to help you with LaTeX formatting, beautiful.
Right.
In fact, there are plugins. I found this plugin. It was free to use for a little bit, and then they wanted that you were allowed to use it like so many times a day, and it built right into Overleaf. And Overleaf is this like online LaTeX. Everyone calls it slightly different. I've heard people call it LaTeX before. Overleaf is this online like editor that's what you use now for doing it, LaTeX. There was a plugin for it that incorporated like ChatGPT, and it would like help with writing and formatting, and it was spectacular. But I wasn't about to pay like $15 a month for it, so I was like, ah. But if you can use it like that, fantastic, like great. Because tables, making tables in LaTeX is like the worst, the one, that is the one thing about it I hate. In fact, I always used to write scripts to make my tables for me just because I was too lazy to type them out. Anyways, any other questions? Nope, okay, awesome. Intro. I'm not joking. This image right here is basically the whole course. This right here this is the spirit of the whole course. If I had to summarize this whole course with one thing, it's this. I'm not joking. If this is the one thing you walk away from, you're all set. Yes, every evolutionary computation algorithm follows the same general idea. There's variations among the bits and whatnot, but this is the general idea. You start with some initialization, randomly generate solutions to some problem. Who here is familiar with the traveling salesperson problem? Conventionally travel salesman problem. This is a very simple problem. It's basically, to explain it mathematically, given a graph of vertices and edges, find a Hamiltonian cycle such that it minimizes the total weights, so it should be a weighted graph. Technically, it doesn't need to be, but typically a weighted graph, such that the total weights in the Hamiltonian cycle is minimized. Long story short, to put it in more reality, imagine you're a salesperson and you're starting in Halifax, and you need to hit, I don't know, Truro, Sydney, New Glasgow, Antigonish, Wolfville. That's your job. You got to hit these places on your sales route. You're going to start in Halifax. You're going to wake up in the morning, and you want to return to Halifax to go to bed at night. What is the order that you go visit these cities to minimize the total distance you're going to travel? Are you going to go from Halifax to Sydney to Wolfville to Antigonish to Truro to New Glasgow? No. For those of you not familiar with the towns in the area, that's a bad idea, right? Let's go to maps. Come on. Well, why? Okay, all right. So you want to start like here. This website is, okay, the computer's having a hard time. So Wolfville, Halifax, Truro, New Glasgow, Antigonish, Sydney, right? So if you want to hit these towns, you're not going to go from here to here to here to here to here to here to Halifax. No, that's a dumb idea, right? What makes more sense is probably maybe Wolfville, Truro, New Glasgow, Antigonish, Sydney, and then back home, right? You don't want to do backtracking and whatnot. That's a traveling salesperson problem, okay? So the idea is, let's say I want to find a solution to that problem, because that's actually a really challenging problem. How about this? Let's start with, first of all, let's envision a version of this problem that has 50 cities instead of 5, like I just showed, to make it a little bit more complicated. How about I start with 100 random cycles, right? For each of them, calculate their total distance, okay? Those that have a shorter distance are better, right? So if we keep taking some of those, well, pause. That's initialization. Randomly generate a bunch of cities. You don't have to randomly generate them. You can generate them with some heuristic as well. But let's say you just randomly generate them, those paths. You pick those, you evaluate. What's their total distance? Those that have a lower distance are better. So I'm going to have this likelihood to select from this population those that are better than the others. Kind of like mix them together, pull them apart, put them over here, and keep doing this until I get 100 more. So the selection is picking those that are slightly better than the others, adding the variation. That's the mixing them together and pulling them apart and putting them back into a new population. And then you repeat that process. Take the new population, evaluate it, select those, put them over here until it's full, repeat, 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 until you decide, I want to stop. Stopping criteria could be after I get a solution that is good enough, after I let it run for so long, after I let it run but it didn't improve after so many times. It could be whatever we want it to be. One of the big lessons of this course is this is the whole idea. If you're doing this, you've got an evolutionary algorithm. It's all of well, how did you do this? How did you do that? How did you do that? Did you add anything else in here for fun? When did you decide to stop? How did you actually initialize it? All of the specifics, that's where it's fun. That's where you get different performances from yours versus yours versus yours. It's all in those details. More significant differences might be okay, there's a genetic algorithm versus particle swarm optimization versus genetic programming versus evolutionary strategies. There's a whole bunch of different types of evolutionary computation, but they all follow this basic idea. So yeah, that's the whole course. We'll talk a little bit about some popular ones, but throughout the course, my suggestion to you is invent your own. And if you're I don't know, here's a crazy idea and it's terrible, if you do the analysis and it's terrible, great, I don't care, fantastic, you did something weird. Maybe it was good, maybe it wasn't, I don't care. It's all about just trying weird shit and seeing what works. That's what evolutionary computation is. That's the whole, people can get nice and academic about evolutionary computation, but the reality is, you're using this on problems where you don't know what else the hell to do. I'm screwed. I don't have a solution to this problem, and I need something, so I'm going to try evolutionary computation. If you're using evolutionary computation, you're already scraping the bottom of the barrel. You're already throwing every crazy idea you have at a problem and hoping something sticks. So try more weird-ass crazy things. See what works, see what doesn't. That's where you have fun. That's where you learn more. That's where you might find some interesting solutions. It really is. Nearly all forms of evolutionary computation follow this idea. Initialize a population of what we call candidate solutions. We're going to go over this terminology a little bit more, and it might become second nature. I will warn you that some of the terminology, people like to pretend we're really strict with the jargon, but we're not. So it could get confusing only because of it being imprecise, but I'll try my best to be precise. So you create a population, that would be like the 100. Each potential path, Hamiltonian cycle, would have been a candidate solution. Evaluate a population's fitness. Its fitness is its goodness metric. So in traveling salesman, TSP, it's the total distance. We want to minimize fitness. Select candidate solutions for the next generation's population. Apply some genetic operators for the variation. That's the variation up here. And repeat until some stopping criteria is met. And this tends to work. It does. As weird as it sounds, it kind of works. It's fun. That's the whole first topic, because that literally is evolutionary computation. That right there is the whole topic, the whole course. Any questions? You're experts now. You know everything about evolutionary computation. Any questions? Yeah.
So when you're thinking of what solutions, so in the selection process, do you always kind of take the greedy approach? Do you always say this one is less, therefore this is the one I take, or do you put some randomness in there too?
The brilliant question. So we will actually talk about this. There's a whole topic on selection strategies. But you can do that. You can always say, just take the top best and do the variation operators. And that can work, but that causes what we call a lot of selection pressure. And that's a fancy word to mean if you're always picking the best, only the best are going to end up here. And the best tend to be similar to one another. So you end up losing diversity in the population, meaning when you're working with these complex solutions, you have these complex search spaces. Has anyone heard the phrase search space before? It's a weird idea. Let's say there is a point in this room, like this ground is level, but there is a point in this room that is actually the lowest possible point in this room. There will be a part that is a little bit lower, okay? If you figure that this room, I do have markers somewhere. I don't know if you over there will be able to see. Can you, if I were to draw here, would you be able to see? Hold on. It's okay. Imagine this room is only one-dimensional, though, for now. Okay? Well, I guess it's kind of two-dimensional, but let's imagine the floor is just this line. And I'm going to exaggerate the highs and lows of this floor. Okay? So the floor might have some slightly higher points, lower points, higher, lower, higher, lower, higher, lower, and so on. Right? We want to find the lowest point. And it looks like the lowest is actually right here. Right? But there's a couple of other relatively low points. Like this is lower than this. This is lower than this. And this is lower than this. And that looks like it's probably a little lower than this. So imagine this even in 2 dimensions, right? Like, you know, it's going to be kind of like bumpy. Right? When you're always picking the best, if you have solutions that are like, if your population is full of things around here, and you're always picking the best, you will, what we typically say, converge on here. And that is what we call a local optimum. Search spaces typically have many local optima, but maybe only one global optimum. So maybe we're okay with this. Maybe we're not. Maybe this problem is so hard that I don't care if this is a good enough solution. Maybe we could have been a little bit more creative and hopefully find something that was even lower. We're going to go into details on this as we go through the course, but very interesting, good question. Any other questions? That was a great question. All right, so what time we got? We are running low, so I won't start the next topic, but what I will say is GitHub. Who here is familiar with GitHub? Who here has heard of GitHub? Put your hand up. Everyone, are you sure? You seem reluctant. You've heard of it, okay. You haven't used it. Raise your hand if you've used it before. Okay, cool. So not everyone. So for this course, we will be using GitHub because that will be how you get the content and whatnot. And you could do it in such a way that you can download all the course content from GitHub by going like here. Come on. And you can download it as a zip. But don't do it that way. We're going to do it with by using GitHub. Typically, now I'm on Windows here, so I'll use like Windows GitHub Desktop. And if you're on Windows, by all means, use it. But typically, I don't really use Windows. Typically, I'm using like Ubuntu more. The only reason I switched back was because this mic that I spent a lot of money on won't work on Ubuntu, despite being a generic microphone, and it absolutely should have, but it didn't, so I was mad. I went back to Windows just for you. So usually, I'd be using Unix, and I would be doing all the GitHub stuff via the command line, via the terminal. I find it a little easier. If you are familiar with the terminal, by all means use it. If you don't like the terminal, you like GitHub Desktop, by all means use it. If you don't know what I'm talking about, you'll see. You'll use whatever you want. GitHub Desktop tends to be a little easier for people, but it wasn't around back in my day, so I go with what I was used to. So this is the whole course content. In fact, this, whatever is here, actually is what deploys to the website. If you go to Site, you will find all of the information for the course website, like outline. It uses restructured text, which then you use this program called Sphinx that actually generates the website. But this right here, let's go to raw. Come on. This is like what I type, and then I run the program Sphinx, and it generates that pretty website that we were just looking at. So this is where that all is. I'm going to be editing this with my office hours and whatnot in class times as well. So that I will be doing that on GitHub after this lecture. Wow, everything's being slow. I guess the university's not used to everyone being on the internet right now. Maybe that's the problem. Let's go back to code. Under SRC, you will find some code. You will find code for an implemented genetic algorithm for solving the n-queens problem, a GA for solving max bit string, a script that holds crossovers, that's one of the variation operators, a selection script, those hold some selection, like typical selection strategies. Mutation, here's a particle swarm optimization, here's genetic programming. This will probably grow. But here's actual working code for a GA solving n-queens. All right, so here's some, look at this. Look how simple it is. And this is me being as verbose as I can in the code to make it like as easy to understand. You could make this even more succinct if you want. So fairly simple stuff. When you make your lecture, you will submit it to the GitHub page. And when I approve it, that's how you know you're getting your marks. And it gets posted to the course website. And it's GitHub. Everything you do is tracked. And if you want a career in this type of stuff, getting on GitHub and using it and showing, look at all the work I've done is a really good thing. People like to see it. So if you're contributing, that's a good thing. So here's a way to get started contributing. Here's a way to get started learning how to use it. But when we start working on some of the code in some of the topics, you will want to like pull from this repo and use the code and then start hacking away and tinker and play and see what happens. This is it. If you do have GitHub, I recommend you already like come along. You can start. You can fork the repo. This is the first year I'm doing it with the repo, so it's bare bones at this point, but it will grow. Yeah. Any questions about that? No. Okay. I guess now is as good as any as a time to stop. Any last questions before we wrap up for today? Who here loves an 8:30 class on the first day of the semester? No one? No, come on. See, that's what I kept telling myself, right? Was like, well, it could be worse. It could be worse. It could be, yeah. All right, cool. We'll stop here.